So now we're going to start to explain the Faraday effect. How does changing a magnetic field make current? So let's start with our setup. You've already got this on your notes, and I'm going to draw it again here. Let's start with our setup where we have a magnetic field that points into the page. There's our magnetic field B into the page. And let's place a conducting bar in this magnetic field. So here's our conducting bar. So there's our setup. Now what we're going to do is take our magnetic bar and pull it to the right with some speed v. So now what we're going to ask is what happens because we've done this. So let's think about any single positive charge in our conductor. So let's just draw a little plus charge. What happens on that positive charge because we've pulled the bar to the right? Well, on that charge, it's going to feel a magnetic force because it's a charge moving in a magnetic field. So every positive charge feels a magnetic force, FB equals QVB, QV cross B. So now we'll ask what's the direction of that force. So we do V cross B to get a force that points up towards the top of the bar. So that magnetic force pushes that positive charge to the top of the bar. So because it feels the magnetic force, it moves up. And where does it go? It goes to the top of the bar. So along the top of the bar, we're going to get a positive charge. Every negative charge also feels a force. So every negative charge has force FB equals QV cross B. Again, Q, so if we have a little negative charge, QV cross B is up, but it's a negative charge, so we rotate our force by 180. Those feel forces that point down, FB on the negative charges. So they end up piled up down on the bottom. So, and therefore they move down. So what does that mean if the positive charges have moved up to the top and the negative charges have moved down? Well, that result is that the charges have separated. Result. Charges separate. So then you might ask what happens because the charges have separated. Well, if we have positive charge here and negative charge here, we get an electric field. So the electric field on our charge would point from the positive charge down towards the negative charge. So our electric field is going to point this way. If there's an electric field from the top of the bar to the bottom of the bar, well, there has to be a potential difference. Because we know anytime we have separated charges, we get a potential difference. So what comes next? Next we'll give the potential difference a symbol. Normally it's called delta V for potential, but the notation started here that we call that potential epsilon, and that equals the size of the potential difference is the electric field times the separation, and the separation is the distance from the top to the bottom, L. So historically, this epsilon was called EMF, where EMF stood for electromotive force. Before they understood the nature of what was happening here, they thought as you pulled it this way, there was a force that pushed it. They didn't recognize that this was a potential difference. So they used to say EMF for electromotive force. Now it's just EMF. So the phrase electromotive force is not really said anymore. Here's something that's really important. We said these charges felt forces when the bar moved. If there was no velocity here, there'd be no force here. So that's pretty important. You only have that induced potential when the bar moves. So that epsilon, that EMF, is called the induced potential, or induced potential difference. And that only happens when the bar is moved. So that was part of Faraday's result, that he only observed current when there was charge, when there was a change in the magnetic field, when there was a change. So the next thing we'll ask is, can we figure out how big this EMF is, how big is this potential difference, kind of as a function of that magnetic field. Let's see if we can sort that out. So I think rather than get to work on that bar again, I'm going to redraw that bar. Maybe I'll even grab a fresh piece of paper. So let's ask, what is the size of our potential difference? So we've got our magnetic field that points into the page. We've got our bar. And the bar is being pulled to the right with some velocity v. We know that the motion causes the charges to feel force, and the positive charges will be driven to the top, the negative charges will be driven to the bottom. Once they get so far apart, we're going to reach a steady state. So steady state happens and when that happens, the charges can't move anymore. So we've got them all lined up here. Once they've reached the top, there's no change in the forces because there's no longer moving. So it tells us that when we get to this steady state, the net force is 0. So we get a steady state, which means that the net force on each of the charges equals 0. So then we'll ask, oh, that blue is a bit hard to see. I'll change to a darker color. So we'll ask, how do we find that force, or that net force, and how do we bring our potential into it? The forces that act on every charge are magnetic force, FB, and electric force, FE. Those are both vectors. They have to sum to be 0. Means that the magnitude of the magnetic force, subtract the magnitude of the electric force, equals 0. Magnetic force, we remember FB equals QV cross B. Here, where everything is perpendicular, the magnitude of our magnetic force will be QVB sine theta, but theta is 90. So the magnitude of the force is QVB. The magnitude of an electric force is charge times electric field, equals 0. What we notice here is that the charges cancel. So that V times B, the speed of the bar times the magnetic field it's in, is equal to the electric field. But a moment ago, we said that the induced potential was equal to the electric field times the distance. Oh, electric field, yes. The induced potential is the field times the distance. So our electric field is our induced potential divided by the distance L, the length of that bar. So we can take this and we can solve it for the induced potential. It's equal to B times L times V. So this is the induced potential when we move a conductor of length L through a magnetic field B with a velocity V. So there's our induced potential. And the induced part is pretty important. It only happens when we move the bar, and by moving the bar, we get this potential created. Okay, in the next part, we'll do a couple of examples.